We know that Balmer's equation can only explain one of the sets of hydrogen optical spectra, while Rydberg's general equation can explain all of the observed hydrogen spectra. And so therefore, the Rydberg's equation is more general compared with Balmer's original empirical equation. Okay, today we'll just continue this story by introducing the quantum idea in relation to this early empirical formula. When we rewrite the Balmer's empirical formula into the Rydberg's equation, we have 1 over lambda equal to a constant, and multiply the two terms determined by integers. So one is n squared, and another is m squared. Okay, so R is a Rydberg constant, and which can be used to describe other hydrogen observed hydrogen spectra even beyond the visible region, such as infrared and ultraviolet regions. So this is a very good empirical formula. Okay, I don't think you can find these details from your textbook, because nowadays people just focus on Borh's theory and Borh's atomic models, but they didn't pay much attention to the original Rydberg equation. Okay, but in my opinion, as I have observed over the years, that actually, if you can incorporate the quantum theory, or not the theory, quantum idea, namely the Planck's formula, into this Rydberg equation, then you can actually achieve you can go very close to the Borh's ideas. All right. Max Planck in 1900 proposed that we can describe the radiation electromagnetic wave in terms of the energy quarter, or energy unit. Now we call it a photon. So the photon energy can be written as E equal to a constant multiply the frequency of the electromagnetic wave. Okay. Now, from the simple relation in the wave, we know that for the visible light, the speed of light, c, can be written as a product of the wavelengths and multiply the frequency, right? So if you combine these two formula, we can get the energy formula for the photon. It became h multiplied c divided by lambda, you see. And h and c are constant, okay? So if you compare with these two formula, you will see that we can rewrite the Rydberg's formula into another form. So if we just combine these two ideas, this is a Planck's idea, and this is a Rydberg's idea, then we can get this new formula if we multiply hc divided by lambda, or equal to rhc multiply n squared minus m squared. Okay. This is a simple mathematical manipulation, but physically we have something new, or some new implication from this new formula, which combines the Rydberg's ideas and the Planck's quantum ideas. Therefore, we know that on the left-hand side is actually the energy of photon, okay, and the photon. So that would be the energy of photon, okay, called photon. On the other side, this energy of photon, this side must be something to do with some change in energy because we are taught this E for energy. So this must be something to do with delta E. Okay, so on this side is a photon. Photon is the energy of photon. Okay. So if you have studied the classical physics, we know that if you want to create something, if you want to create some energy, then some system must lose a certain amount of energy. Okay, so if you rewrite this formula into the energy formula, that would be photon P, that is photon energy, will equal to the change in energy. Okay, so in this case, what is the E? There are two ways to write the E, right? One is simply written as E can be written as just RHC divided by N squared, or you can read it as negative RHC divided by N squared. That will give us a hint that this expression, namely R multiplied HC divided by N squared, actually represents the energy. Can we just put the N here to denote this energy? And this energy is discrete, okay? Can you see that? So if you draw this diagram, if that's what I did many years ago, I'm just curious about these two formulas. What I can do, I can just draw the graph. So this is energy. This is both are possible. Okay, we don't know exactly. So this is En, and this would be the N. So that would be the N, the integer. So this is a 1, 2, 3, 4. 1, 2, 3, 4. Can we call this E1? So this is E1. And so this is first dot. This is the first energy. The second energy will be 1/4. Can you see energy versus half? This is 1/4. So that would be the second. That would be the E2. Can you see? E2 decrease. How about E3? That would be 9th of the initial energy, so somewhere here. Okay. So in this way, we can draw a trend line. If I draw the trend line here, we will see that the energy will obey this inverse square root law, you see. So the inverse law, inverse square law also appeared in this context of optical spectroscopy. In other words, the energy, in this case, energy N is proportional to 1 over N squared. Alternatively, we can consider this formula, the energy they represent is negative. Okay, so if that is the case, we can draw the similar diagram. Can we call this is negative E1 when N equal to 1? That's negative E1 here, and this is N equal to 2 is 1/4. 1/4. So the negative. So negative E1 divided by 4. That be the second point here, third point, and fourth point. So we have two alternative energy graphs, simply based on combining the Rydberg's equation with Max Planck's quantum theory, namely the formula for the photon energy. You can use this trend line for if the energy is negative. We don't know which sign shall we use, but both of them can explain this simple fact that energy of the photon can be related to the change in some type of energy. Okay, and this energy must be associated with atom. It's logical. Okay, it's natural to assume that energy actually belongs to atomic energy. atom, the energy of atoms. Okay. This is something, of course, I did, okay, and many years after I started quantum mechanics. But in history, Niels Bohr was the first person thought in this direction. So basically, we have two forms for this energy relation. The photon energy can either be written as, can we just use RH, R? We can use written two form. Either we use this RHC n square minus and RHC m square, or we can written as a negative RHC m square, take away of negative RHC n square. Okay, so both are correct. So both the formula are correct, are consistent with this called the modified Rydberg equation. If this formula is correct, so what can we say about the structure or the energy formula of atom? Because after all, in this experiment, there's nothing in between except, see, in here, this sun ray, there's nothing in between except the hydrogen, the pure hydrogen gas. So therefore, this term, if that term actually represents the energy, this term must be the internal energy of hydrogen atom. Okay. Of course, if you can go that far, you would have, get a Nobel Prize before Niels Bohr. Okay. I will stop here.